This research was funded by Urban Mobility and Equity Center, UMEC, and also IGAP grant, supported by Morgan State University. The original research started May 2017, and for the continuous research, we got the IGAP grant from Morgan State University last year. And the first phase was completed about 2 years ago, and a current phase will be ending by this December. This project is actually for developing algorithm. I'm going to show you several different algorithms today, but a series of the optimization problems and its impact to improve feeder bus transit system. This presentation can be a very technical, but I'm trying not to be very technical and trying to introduce the broad aspect of my research. If you are interested in technical aspect, then you can contact me for the further information, or you can find our papers or presentation materials or a research report. The research motivation was actually I've been always interested in urban public transportation. However, in the United States, it's difficult to provide a good accessibility for transit riders, especially for a suburban or rural area people because of the lack of good accessibility. So we need a good fast first and last mile service, or mobility as a service, or some kind of a connection between their origin or destination to a fixed route transit system. So some transit agencies in the United States are working with TNC companies, but it costs a lot. The fixed route feeder transit service, which connects from a origin destination to a major transit service, cannot be very efficient in rural or suburban area due to the low demand. So probably demand responsive service can be a better choice. Also, even if we provide a demand responsive service, human-driven feeder bus service can be less cost-effective due to the low vehicle capacity. The one human driver can pick up and deliver few people to the transit station, and it can be very costly. So that motivated us to think about in the future, if automated transit service, automated vehicle is available, probably we can provide some kind of a demand responsive transit service with the current good communication technologies that we can find from TNC companies. When we try to use Uber or Lyft, something like that, we type origin destination, and then the communication technology enable the companies to connect vehicles and people who wants to use the service. So once automated vehicle becomes available, we can make some kind of automated demand responsive feeder transit service to support first and last mile service, which can be a much more cost effective. However, this a developed algorithm can be also used for the human-driven demand responsive feeder transit service as well, because we want to improve a demand responsive feeder transit algorithm for different situations and different constraints and so on. As I mentioned, the first phase, a report was published by which is supported by UMAC, was published 2 years ago. We already published 2 papers from those research for algorithms and impact of automated vehicles on optimal demand responsive feeder transit, and also multiple papers are under review right now. We presented more than 5 research topics at different conferences, including TLB 2018, 2019, and demand responsive, a conference in Baltimore last year, and so on. So today, as I said, I'm not going to be very technical, but I'm going to discuss different applications and impacts by this research. First, I'm going to talk about feeder bus routing for long headway trunk line. Here, trunk line is like a metro or LRT or regional rail or express bus services, the major trunk line that a lot of people are using it. But it is difficult to go to this major transit. It's difficult to access to those major transit lines from a suburban or rural area. So how are we going to provide a good routing for long headway trunk line? Also, we're gonna talk about, instead of picking all individuals, how about providing a temporary stops? So people can go to those temporary stops, and the feeder bus just collect people at the temporary stops based on a requesting people. Also,
Dr. Lee, sorry, this is Anam. Sorry to interrupt. We still see your first slide. You're not moving your PowerPoint. You're not moving to the next slide.
It's still first?
Yes.
Oh, so you cannot see the second?
No, still the title.
Oh, sorry. Okay. How about this? Can you see it?
Yes. Now it's moving.
Do you see mine? My face? The second page?
Yes.
Oh, then probably, I'm going to use this, I don't know, slideshow may not work right now. I don't know why, but if this is okay, I'm going to use this slide.
Yeah, it's big enough.
Yeah, thank you, Anam.
Sure.
So here again, me and Amireza. The third slide, I talk about funding sources. At first, I talk about research motivation. And we published a report. These are the 2 journal papers, and multiple papers are under review. There are 5, more than 5, actually 5 presentations from this research. So here, first is the basic algorithm for long headway. I'm going to talk about what makes the long headway trunk service, algorithm for those services different from different situation. But well, the first one is a long headway, for the long headway trunk line. And then I'm going to talk about what if we have temporary stops for picking up passengers and dropping off passengers, impact of automation on feeder transit network, impact of degree of circuity on feeder network, sensitivity analysis for feeder network, and also feeder bus routing with short headway trunk line. So these are a series of research that we did from these fundings. A demand responsive feeder transit service is, as I mentioned, it is complementary mode to connect from origin destination to the major transit network. Again, a feeder bus is maybe very necessary for urban, suburban, or a rural area because a lot of people are spreading in those wide areas. So it's difficult to access. Because of that, people use park and ride or kiss and ride. But if we have a demand the feeder transit service, that will be more economical and environmentally a better, and it can save energies, and also it can promote equity because the people who doesn't have cars or who doesn't want to use cars for their commute, they can use a feeder service and major transit route. So this, as I mentioned, this feeder transit service can improve accessibility and transit ridership, and also it can reduce a travel cost for many people. Okay, and if automated vehicle comes out, in reality, it can save cost more as well. The first that we thought about is how to make a feeder transit network algorithm more efficiently, including considering many different constraints. So a well, when we thought about it, basically we thought about three major algorithms. The first one is for suburban and rural area, which has a usually long headway trunk line, like for example, in Baltimore LRT, the headway is about 20 minutes or 30 minutes. Regional rail in many cities has a longer headways. So we thought about making a good algorithm for long headway trunk line is necessary. And then going to the next a thought process was, well, instead of picking up all those people, the suburban area has the people lives not very close nearby, but if we gather those people in certain a meeting point, we call it temporary stops, then the bus can go through the temporary stops instead of picking up and dropping off a individual people. That can make the service more efficient. The final a puzzle was a feeder service for urban area with a short headway trunk line. In many major cities, the metro is, the headway is 3 minutes or 5 minutes, very short. The major difference between long headway and short headway is the long headway, the feeder bus can leave and come back by the next 8 train because the headway is 20-30 minutes. So it's easier to make the algorithm. For short headway, the train comes every 3 to 5 minutes. So the bus cannot return for the next train. So then we have to think about when the feeder bus needs to come for the to be connected with a major rail service. So the approach to the algorithm is a different between long headway service and short headway service. So those three is a main a development in terms of algorithms. We did some background, literature reviews, the feeder bus concept has been here for a long time. So, well, because it's not slideshow, it's difficult to show. Slide, well, I will send this a slide to you so you can look at it. But basically long time ago, a feeder, a transit route, a study was limited to a single station or single train, but multiple stations and so on. Now, in our research, what we want to do is we want to handle multi-station, multiple buses, multiple trains with a relocation of feeder buses between stations, and also considering individual passengers' travel time. So, well, feeder bus service is like a traveling a salesman problem. So if a certain passengers are picked up first, then they have to be in the vehicle longer time, even if they are close to the station. So we want to minimize a individual travel time as a constraint, and we develop the algorithm based on that. So here is the basic innovations from this research. We allow relocation of vehicles from the feeder buses from station to station, depending on the demand distribution. For certain time and certain trains, for certain station, there can be more than usual passengers. Then we want to relocate feeder buses from different station to that station. So that will maximize the efficiency of fleet usage. So we allow relocation of vehicles. We consider individual passengers' travel time, because usually optimization problem is to minimize total travel time or total cost. Minimizing total cost is important, but also we want to maintain certain level of service to individual passengers. The temporary stop is one of the algorithms that will be connected to a feeder bus algorithm. Then we evaluate impact of those automation of vehicles. If the feeder bus becomes automated, how much cost we can save and so on. Also, we evaluate those individual passenger, considering individual passenger travel time will change the feeder bus network, how it will change the feeder bus network. Also, we develop a short headway trunk line algorithm, which is the most complicated algorithm in this whole research.
Yeah.
So, as I said, again, there are three major algorithm development: long headway with temporary stops, and short headway feeder bus services. So to explain this algorithm a little bit, this is a conceptual figure. So assuming that we have 4 stations and different times, and the first train will come, first station, second station, third station, and fourth station, and the train will go second train, third train, and fourth train. The feeder bus will leave this station, pick up from the first train the alighting passengers, and then while the bus drop those people, they pick up the people for the second train, and then the feeder bus will come to the a station one again for the second train. So that is the feeder bus a movement unless they need to relocate, and when the trunk line has a long headway, 20 minutes or 30 minutes, for example. Then feeder bus travel will be 20 minutes or 30 minutes. They will pick up and drop off passengers and return to the next train. If necessary, they will go to instead of a, a, a station, the feeder bus which left station 3 can go to station 4 if a relocation is necessary. So this is the simple flow chart for the algorithm. Well, again, I'm going to skip most of part for this technical part. So this is the simple presentation of the result. The upper figure shows the distribution of the passengers, boarding people's origin, and alighting people's destination. And these are the train stations, the yellow square. And then our algorithm made a routings, feeder routings. The feeder bus leaves the station and a drop off and pick up and come back to the station for the next train. Here, this dot line shows the relocation. So the bus which left station 2 drop off and pick up and then go to a station 3 instead of station 2. So our algorithm handled a feeder bus network successfully, considering relocation and individual passengers' travel time. Next, a algorithm development was how to find a optimal temporary stop locations. So we group the passengers, boarding and alighting people, and then we create temporary stops for clusters of people, and bus leaves the station, and then it'll go to the temporary stops, pick up and delivering, pick up and dropping off passengers at temporary stops, and come back for the next train. So it is a long headway for the long headway trunk line service, and instead of picking up passengers individually and dropping off passengers individually, we go through the temporary stops. However, if certain passengers are totally separated from these clusters, then we allow buses to go through the individual passengers' origin and destination as well. This shows how do we make a clustering algorithms. And then this figure shows similar to the first a algorithm input in page 19, but we try to make clusters. So we could save here. There are trade-offs. Well, people needed to walk, so their walking time increases, but their in-vehicle travel time decreases because the bus doesn't need to go every corners, and also bus operating cost was reduced. So there are trade-off between walking time and in-vehicle time plus operating cost savings. The total cost was decreased, but again, that'll depend on demand distribution. So how much cost we save, that will depend on a demand distribution, but it is worth to think about if a lot of people stay close within certain clusters, then this can be very effective. I'll go to the final well, I decided to move a little bit. The third major algorithm is for the short headway trunk line. Again, as I said, this can be much more complicated than first algorithm, because first algorithm, we assume that bus will come back for the next train. So the algorithm needs to match between bus and passengers, and bus and stations when we decide relocation. However, bus is supposed to come back for the next train, so we don't need to match bus and train. But for the short headway trunk line, bus can be come back for the bus which left for the first train, can come back for the second train or third train or fourth train, depending on which passengers we pick up. Passengers needs to come back before their supposed departure time at the train. So they have some kind of travel time windows. So as long as they are delivered before their a departure time, it was acceptable to come to the station early. So we need to match feeder bus and train at the same time. So this algorithm becomes much more complicated. And also we allowed relocation, just like here, this is conceptual diagram, but the bus which left at station 4 for the train 1 can come back for the train 3 for train 5. So it is much more complicated than long headway trunk line. So this is we need this shows a flow chart for the algorithm. This has 2 separate algorithms to make this a algorithm. And then this is a result. I guess we missed to include input file here, but this is showing that the feeder bus which left the first train will come back for the third one. And well, for here, this different color shows the buses. So bus number 1, bus number 2, bus number 3, and so on. So the bus can come back for the different trains. Sometimes the bus comes back for the 2 train later. sometimes 3 trains later, 5 trains later, and it can relocate from station 1 to station 2. So this algorithm handles feeder bus network with a short headway trunk line, considering relocation and individual passenger travel time. So these 3 are the major developments in terms of algorithm. And then we also, using this algorithm, we evaluate impact of different inputs to the feeder bus algorithms. So this is very short a diagram to show the result of impact of automation on transit routing. Well, actually nobody really knows how much will be the cost of a automated vehicle operation. We went through the different literatures. This paper will be published soon. It was accepted, so you can. Also this is also in the similar contents is in our report for UMAC. So you can find out our literature review how to estimate the cost for automated vehicles for feeder buses. But most of study mentioned that the operating cost will be reduced because it'll eliminate or minimize the human labor cost. So here, the $5 per kilometer is our basic operating cost for human-driven vehicles. And then we reduced cost for $4, $3, $2, and $1. This red line shows total cost when feeder bus network is optimized. Of course, the unit cost is decreasing, so total cost will be decreasing. That's obvious. This green dot line shows total bus operating cost. So that is decreasing almost parallel. That is obvious. However, if you look at this purple line, this is total operating cost per unit operating cost. So this total operating cost per unit operating cost is increasing a little bit, while total passenger travel cost decreasing a little bit, which means if we can reduce unit operating costs, that means we can optimize a feeder bus network in favor of more passenger travel costs. Because, well, here, when it is $5 per kilometer, the operating cost is bigger than travel cost. So the optimization process tried to minimize operating cost more than travel cost. Well, when the operating cost reduced, then optimization process tried to minimize passenger cost more. So if a automated vehicle feeder bus becomes available, then the optimal automated feeder bus network will decrease not only operating cost, but also passenger cost, travel cost as well, if we optimize the feeder network. These two lines shows that this brown dot line is total passenger cost, a total it's total, I think, total cost based on 5 kilometer total cost with 5 kilometer network. That means we made the optimal network based on 5 kilometers, and then we didn't change the network, and we assigned the passenger, and this is the cost. So if obviously the difference is savings by the a optimization process based on a automated vehicles. That is about the savings for passenger travel time. The next a research was to find out impact of individual passenger degree of security. That means, well, degree of security is the ratio between the people's shortest travel time and their actual travel time. So this, when it becomes 5, that constraint is totally relaxed, which means we don't care how long the passenger in the vehicle spend time in the vehicle. 5 times more than their shortest travel time is DOC 5. DOC 3 is we limit the passenger travel time up to 3 times of their shortest travel time, and so on. We optimize the feeder bus network based on this constraint. Now, about 2.5 or more, the passenger total cost was decreased a little bit, but not significantly. That means, well, if without this constraint, optimization process will find real optimal solution to minimize total cost. And they don't care whether some people will spend 5 times or 4 times of their shortest travel time in vehicle. But using this, from this diagram, for this particular example, well, if after 2.5 of a degree of security, the a decrease in total cost was minimal, while still some more people has to spend a lot of time in the vehicle. So, well, of course, if we give a too low degree of security, that will increase a lot of travel time. So that is not probably good, because the feeder bus system will require a lot of buses or less optimal solutions. But after 2 or 2.5, the decrease in a cost is minimal. So probably the conclusion was transit agencies needs to consider this kind of constraint to provide everyone's maximum travel time in the vehicle. So here, about 2 or 2.5 of degree of security may be a best degree of security constraint, because it'll satisfy almost all the people not spending a lot of time in the vehicle, but at the same time, the cost reduction is minimal. Also, we conducted several sensitivity analysis, changing demand, vehicle capacity, and fleet size, and so on. Here, it shows that the increase the passenger demand, increase the passenger demand will have more economic impact on the transit operator when they use a shared automated vehicles. So, in conclusion, this research conducted 3 major tasks in developing algorithms for a demand-responsive feeder transit services to consider many realistic constraints, including relocation of the vehicles or maximum travel time of the vehicles, the passengers, and so on, for different situations such as long headway, a trunk line, or short headway trunk line. And also we consider the temporary stops. The relocation and individual DOC is it's kind of a very new concept for this demand responsive feeder transit system from the past studies, especially for a short headway trunk line. The impact studies, like impact by the automated vehicles or impact by the individual degree of circuity or a sensitivity analysis, those analysis can be useful for transit agencies when they decide whether they want to go for the automated vehicles or whether they consider maximum travel time for the passengers or whether they want to increase fleet sizes or bigger buses and so on. So those will be also useful for agencies. In addition to the algorithm itself, the algorithm can be useful for transit agencies when they consider providing feeder buses on demand responsive feeder buses. So this is about my presentation. Thank you for your attention. And again, if you send me an email, I will send you this presentation files. Also, again, some of the papers or presentation files and research report for UMAG is available. Any questions? Hello?
Dr. Lee, this is Anam. I have a quick question for you. Thanks for the presentation. Yeah, when you were talking about that geographical distribution of demand, did you actually do a cluster analysis? If yes, what was the attributes you used in the analysis? I was wondering if it's just a visual representation of the data points or you actually did cluster analysis.
Well, we distribute this demand randomly, including their GPS coordinates and their arrival, a preferred arrival time or preferred departure time and so on. We did a cluster analysis when we consider a temporary stops. Here, my student Amireza is here. Amireza? Amireza?
Hello? Hello, yes.
Yes. If you have
Anna, yes, I have actually heard this question. I don't know, you have my voice or not? Do you have my voice?
Yes, we can hear you.
Okay.
Yeah, thank you.
Yes.
Go ahead.
So yes, we actually do for actually both of them, because the location of the passengers are mm, random actually, and we first actually cluster. This is the first actually part of the actually model that actually group actually series of actually passengers for each vehicle, right? And yes, this is the first part of the model.
Okay, thank you.
No problem.
Any other questions? Any other questions? I just look at the, well, I didn't have time to look at who's here. And there are some guests from long distance. So thank you for joining. Any other questions?
Well, thank you, Dr. Lee. Good presentation. I enjoyed it.
Thank you again.
Hello, can you hear me?
Yeah, sure.
Oh, yeah, no, you finished Dr. Lee first.
Yeah, again, if you want to look at this presentation file, then send me an email. In the email, there is more information about detailed research product papers and reports and presentations. So probably if you have a technical questions, probably you can go through those papers and presentation files, and then still if you have questions, you can contact me or Amireza for the detailed further questions.
Thank you, Dr. Lee, for your great presentation, and thank you everybody for joining us
Thank you.
For our webinar that was 4 hours long, and we recorded and we will make the video available for anyone that needs it, and hopefully we will have another webinar sometime in near future for our other UMEC related grants and studies. Thank you, everyone. Have a great day, and we'll see you later.
Thank you.
Thank you, everyone. Thank you for giving the invitation.
Okay.
Oh, Dr. Ahmed, how are you?
Fine, fine. How are you? We are still doing well. Nice to
It's
hear
been
from all of you.
Yeah, it's been a long time, my friend. It's been a long
Right.
time.
Right. Yes, Dr. Saka. Yes, I am very pleased to hear from you.
Yes,
Okay.
good. All
I
right.
look forward to meet you again.
Sounds
Okay.
good. That sounds good.
Yeah.
All right.
And
Okay.
thanks for inviting me. Okay.
Oh, anytime. Okay.
Thank you for joining.
Okay, sure. Okay. All of you stay safe. Okay.
You do the same.
Okay, thank you.
You
Thank
too.
you.
Bye, everyone.
Bye.
Bye.
Thank you, and
Bye.
bye. Bye-bye.